These are the problems that we're doing for Monday from the finals review packet. If you're an online student, you can access the packet directly from the course website. They are posted on the course website in the week 16 materials. So if you are an online student, that's where you would go to access this. And obviously, if you're here on campus, I gave you a hard copy. What we're going to do today is we're going to do the problems for Monday of finals review. So the problems are listed by day. And just as a disclaimer, this is not a guarantee of what's on the final. Right? To know with confidence what's on the final, you should consult the finals review. You should consult the outline, okay? Because the outline states exactly what's on the exam. So these are the problems for day one. There's my disclaimer, right? The outline, which is posted on the course website, states exactly what will be on the test. These are just problems that I thought you could benefit from seeing. All right, so let's go through these. Let's go through these. For barium, barium has 56 electrons, right? If I asked you to do the long version, that's a long electron configuration to write out. But to use a shortcut, what do? I go up a row to the end, right? So what element is in brackets? Xenon. And then all I'm dealing with is the leftovers, right? So what would that give me? 6s2. And that's it, right? That's all I have to do with the shortcut. Remember, these are the core electrons, these are the valence electrons. Is everybody good on this one? All right, let's do nitride. Nitride is N3-, right? So on the periodic table, we find nitrogen. Now this has 3 extra electrons, right? Because this has a -3 charge. So are we going to treat this like it's beryllium, or are we going to treat this like it's neon in terms of the periodic table version of writing the electron configuration? We're going to treat it like it's neon, right? Because it's got 3 extra electrons. So you can write, I didn't specify either long or full, full or shortcut. So you could do either one since I didn't specify. So if you're doing the full version, you would do 1s2, 2s2, 2p6, right? That would be the long version. Or you could also have written helium, really doesn't save you a whole lot, right? 2s2, 2p6. Both work. Do we agree? All right, copper 2, Cu2+. Has this gained or lost electrons? This is lost. So we find copper. Copper is one of our exceptions, copper metal, right? That's one of our exceptions we actually have to use. It's one of the anomalies. But this is copper ion. So what element are we treating it like? Are we treating it like it's cobalt, or are we treating it like it's gallium? We're treating it like it's cobalt, right? So let's do the shortcut. What goes in brackets? Argon. Then what? 4s2. Then what? 3d to get to cobalt. 1, 2, 3, 4. I read that part. 1, 2, 3, 4, 5, 6, 7. Yeah, I agree. Do we agree? Yep. And then oxide. Notice it's "ide." So that's oxygen ion has what charge? -2. Just figured out why that door's clanking around. Because it's not closed. Okay, this has it's gained 2 electrons, right? So are we treating it like it's carbon, or are we treating it like it's neon? We're treating it like it's neon. So what's its electron configuration going to be? Something we've seen before in the last 35 seconds? It's going to be same as this, right? It's going to be isoelectronic. 1s2, 2s2, 2p6. Or if you want to write the shortcut, it doesn't really save you much. 2s2, 2p6, right? These are isoelectronic. Right? Iso meaning same. Okay, this is a really common mistake that I see students make, differentiating between ions versus isotopes. Similar sounding, different meanings. What's the difference? Let's talk about what an ion is. An ion is an atom that has what? Right, an atom that has gained or lost electrons, right? Whereas an isotope is what? Right, atom that's gained or lost neutrons, right? This does not affect the nucleus, right? An isotope doesn't affect the nucleus. Right? That's not a nuclear change. Whereas this is a nuclear change, right? This affects the nucleus. Difference between one affects the nucleus and one doesn't, right? Are we good on number 3? All right. I'm gonna erase it. Move the screen up. All right, let's do number 4. Orbital diagram. Now I've given you the boxes. I'll usually give you way more than you need. I actually gave you just enough for this one. Because calcium's got how many electrons? 20. Right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Right? Normally I'll give you way more than you need because I want to make sure that you know where to stop. Right? But this is the exact same information as the electron configuration. Because if you write the electron configuration, it'll be the exact same thing, right? Because if we're doing calcium, that will be argon. And argon takes care of everything up to here. And then all you're left with are the leftovers. So it's the exact same information as an electron configuration. Just be advised, don't expect me to give you the exact number. It's probably going to be way more than you could possibly need. All right, let's fill out this chart. This is something we did at the very beginning of the semester. What element is Mn? Manganese. Okay, how many protons does it have? How many? 25, right. I couldn't really hear you. How do you know? The top number, the bottom number? Right, this is always the atomic number, so that's 25. How do you get number of neutrons? Subtraction, right? So how many would that be? 30. And then how do you get electrons? Right, this isn't an ion, so 25. And then how would you write this in hyphen notation? Manganese. Right, manganese. And then you put a dash, and then 55. It's always the mass number, right? Because if it were the atomic number, you'd never be able to differentiate between isotopes. And isotopes have different mass numbers, right? That's why you put the mass number here. So for instance, carbon 12 versus carbon 13, right? You put different mass numbers there to differentiate between isotopes. Okay, we can figure this one out by giving number of protons. That's something we can solve. How do we figure out the identity just from the number of protons? We got a table, right? What's element number 50? 10. Okay. Let's write our nuclear symbol so that we can figure out this part more easily. If we're writing 10, what's its symbol? SN. What goes on bottom? 50. And what goes on top? 119. And how'd you get that? That's just the mass number, right? 10's mass number is 118.710. We round it to the nearest whole number. Okay, so now we're ready to do our number of neutrons because this is set up nice and neat for us. So how many neutrons does it have? 69. And how many electrons? 50, right? This isn't an ion. And so how will we write this in hyphen notation? 10, 119. Are we good on number 5? Questions on how we did number 5? All right. All right, let's move on up. All right, number 6 is an explanation from the beginning of the semester. Right? If I don't need to do a demo to show you this. You imagine a glass of water and you imagine throwing some ice cubes in it. What happens to the ice? It floats. All right, so why does ice float on water? And why does anything float on top of anything? Right, floating means lower density. Okay, well that's great. What is it about water that makes its density go down when it freezes? Because that's not what you'd expect, right? For most substances, the solid phase is more compact than the liquid phase. But in water, it's one of the unique things about water, the solid phase is actually less dense as opposed to more dense. So what causes that? Who remembers? If this is H2O in the liquid phase, now you're gonna have to bear with me my sad drawings. There's solid, there's liquid. Particles in the liquid phase, H2O, what IMF are we experiencing here? What? London and hydrogen bonding, right? That's the big contributor. So in the liquid phase, right, they're all really close to each other. Particles in the liquid phase are really close, yes? Now, one of the neat things about water is that when it freezes, the crystal actually expands. So the crystal lattice for water kind of has a hexagonal shape. And so it's just layers and layers of these hexagons. Right, just layers and layers and layers and layers and layers of these hexagons. So what you're doing is you're taking the same mass and you're spreading it over a greater area. In other words, the volume increases. All right, so if you take the same mass and divide it by a larger denominator, your density goes down. And that's one of the unique things about water. Questions on 6. All right, let's talk about 7. The principal quantum number n can be any integer but 0. Why? Why can't the principal quantum number be 0? Why is that? There's not a 0 level energy level, right? If I said, okay, draw a circle with a radius of 0, you wouldn't draw a circle, right? There's no such thing as a level 0 energy level. That would be a circle with a radius of 0. That doesn't make sense. The magnetic quantum number m sub L, and I usually put this in cursive just so you know, I just got lazy. All right, so you can tell it from a 1. The magnetic quantum number can be integer values from what? What's the range for m sub L? Negative L to positive L. That's right. All right, let's move along. Okay, let's draw these orbitals, and again, I would put this in cursive on the test. I just got lazy. Didn't go back and change the font. Let's decide if this is an allowed set, number 1. Now, I just gave you n and l. right? I didn't give you M sub L and M sub S. So if N equals 2, can L be 2? No, right? Not allowed. There's no orbital. Why? Because why? Right, L equals integers up to N minus 1. So if N equals 2, then L could be what two values? 0 or 1, right? It couldn't be 2. So there's no orbital that could form there. Not allowed. Trick question. All right, what about B? We gonna get anything there? No. Why? N cannot equal 0. Right? Okay, what about N equals 6? If N equals 6, can L be 0? Yeah, what would that be? 6s, right? Let's go back to our little chart. 0, 1, 2, 3, S, P, D, F. That'll be 6s orbital. Do you have such thing as 6s? Look at your periodic table. Yeah, 6s exists. So what would 6s look like? How would you denote that the N is 6? 6 tick marks, right? All right, and then what shape is this? It's going to be a circle. So just do your best. Not going to get out a protractor and make sure it's 100, perfect 360. I had a board there, so mine looked really sad. All right, can we have D? Does D exist? Right, and why? Right, it's the same reason as in A, right? No orbital. Because if N equals 1, then L cannot equal 1. L equals 0, right? Max value of L is N minus 1. Any questions on 9? Okay. Last one. Oh, second to last one, sorry. List the possible sets that can produce 4D, including M sub S. All right, so if we've got 4D, what does that mean L is? I mean, excuse me, what does that mean N is? 4. And what does that mean L is? Right, 0, 1, 2, 3, S, P, D, F. That's 2. So that means that M sub L follows into what range? -2, -1, 0, 1, 2, right? And we are including M sub S. We are including M sub S. So how many sets are we going to have? 10. We'll have 10 sets, right? 10 total sets because we're including M sub S. If we were not including M sub S, it would just be 5, right? But because we're including spin, we're going to have 10. So N, L, M sub L, M sub S. So N equals 4, L equals 2, M sub L equals -2, M sub S equals -1/2. Now we do that all again. 4, 2, -2, +1/2. 4, 2, -1, -1/2. 4, 2, -1, +1/2. 4, 2, 0, -1/2. 4, 2, 0, +1/2. 4, 2, 1, -1/2. 4, 2, 1, +1/2. 4, 2, 2, -1/2. And 4, 2, 2, +1/2. All right, you have to have all 4 for it to be a valid set. So all 4. Do we agree on number 10? Okay, last one. How many sets produce 5p excluding M sub s? So our work is a little less this time. 5p. All right. If we've got 5p, what does that mean N equals? And what does that mean L equals? 0, 1, 2, 3, S, P, D, F, right? L equals 1. So M sub L is what values? -1, 0, and 1, right? Now we're excluding M sub S, so these are not technically full sets, right? We're just making our work shorter. So how many sets do we have? Just 3. Right? Because we have 5, 1, -1, 5, 1, 0, and 5, 1, +1. Right? If we included M sub S, we have 6 sets, but because we don't include M sub S, we only have 3 sets. How do we feel on the day 1 problems? Questions? All right, that's where we'll stop for today.